Alright, hey everybody, we're ready for a new beautiful, wonderful video here over confidence intervals, and this time we're going to be looking at confidence intervals for the difference between two proportions, and a little bit later on we're going to look at the difference between two sample means. Now the idea is in a sampling distribution, remember you know the true P and the true Q's for samples, so if you have a true proportion of men who wear their seatbelt and a true proportion of women who wear their seatbelt, and you look at the difference, well then you know the expected difference. You know the true difference between men and women who wear their seatbelt. Let's say it's 6% difference. Women are more likely to wear their seatbelts, whatever. Well, sometimes we have no idea what the difference between two proportions would be, so we have to run a confidence interval to try to estimate from a sample what that actual difference could be. So there's not a whole lot that we need to do this. The first thing we need is one sample. We need a first sample, and then we need a second sample because we have two samples, and we're looking at the proportions of two samples, and then we're looking at the difference between them, so we subtract them. It's that simple. It's pretty easy to find the difference between your samples. Now we need the standard deviation because we understand that this difference between our samples, well, it's just our samples difference, right? Somebody else's sample difference might be a little bit different, so there is going to be some variation here, and we would like to use standard deviation, but unfortunately we're going to have to use standard error, and that's because all we know is p hat in P1 hat and P2 hat. We don't know the exact true P's. So we're going to use P hat 1 and Q hat 1 divided by sample size 1, and P hat 2 and Q hat 2 divided by sample size 2. Now if you look into your sampling distribution cheat sheet, you'll see that that is the same formula, but if for standard deviation it uses P's and Q's, not hats. Okay, so those are pretty much the only two things you need. You need the difference you observed, and you need that standard error, and it's pretty simple from there. Don't forget to check your conditions. That's the first thing that you should always do. And it's a little bit more time consuming here because you have to state that both samples are random, both samples are less than 10% of their respective populations, and both samples need 10 successes and 10 failures. So you do have to check that work. Your work is basically going to be showing the p hat and the p hat for 1 and 2, showing your standard error formula right there, and then after that the interval is really easy. You just take your observed difference, and that's the difference that you saw, and then you're going to plus and you're going to subtract, or you're going to add and you're going to subtract. Whoa, what am I doing? That's completely wrong. You're going to add or you're going to subtract your margin of error. And your margin of error is going to be calculated by the z star, so it's still z star here, that doesn't change, so 1.96 for 95% confidence and so forth, and then times your standard error of your difference between your samples, and that was of course calculated right there. So it's pretty easy, and then don't forget you need that nice third conclusion still. So not really a whole lot of work goes into these problems. Hopefully everything makes sense to you right there. So let's just jump right into a problem here. So to determine if men or women are more likely to wear their seatbelts, a study of 160 random men and 195 random women was conducted. Of the men, 115 wore their seatbelts, and of the women, 157 wore their seatbelts. Construct a 95% confidence interval for the true difference, sorry for the typo there, between the men and women. So let's get started right away. The first thing we need is we need two p hats. We need a p hat for the men, and I'm going to use a little m for men, as opposed to something generic like 1 or 2. And the men, remember, was 115 out of 160 men wear their seatbelts. So that's 115 out of 160. That's 0.7188. 0.7188. And we also need a p hat for the second sample, and I'll use a little f there for females, or you could use a w for women if you would like. And that was 157 out of 185. So that's 157 divided by 185, and that is 0.8486. 0.8486. So we notice right away that women were higher than men. Females were higher than males. But is that always going to be the case? Does that necessarily mean the true difference is that? Well, that's what we have to find out. So I like working with positive numbers. Technically, you can get negatives, it wouldn't matter, but I am going to work with the positives. I'm going to do the females minus the males here, and it's going to be 0.8486 minus 0.7188. 0.88, and I get a difference of 0.1298. So I get observed difference of 0.1298. So roughly a 13% difference between men and women, but is that always going to be the case? Is that the true difference between men and women? Well, I don't know. That's why I want a confidence interval to try to clarify this up for me a little bit here. Now I'm ready to start doing my work, but again, always make sure we check our conditions. So remember, the P's hats and the two P hats are really all you need to get the problem rolling, but I do want to check my conditions. Both samples have to be random, both random, and I'm being a little, I'm doing what you shouldn't be doing, but make sure you kind of write in full sentences here. Both samples are less than 10% of the population. And we also need to have the 10 successes and 10 failures for both. So obviously for men, I had 115 successes, and then 160 minus 115 is 45 failures. So that checks out for the men. For the females, I had 157 successes. That checks out. And 185 minus 157 is 28 failures, so that checks out as well. So I did have my 10 successes and 10 failures. All right, so really the only other thing I need is a standard error of the difference, and this is going to tell me that, hey, you know, my difference might vary from somebody else's, and the formula is going to be a little bit time consuming to write here, but it's going to be 0.7188 times the opposite of that, which would be 1 minus 0.7188, 0.2812, divided by the sample size for men, and that was 160, plus, now we got to do the women here. The women were 0.8486 times the opposite of that, so 1 minus 0.8486, and that's 0.1514. And when you type, and again, that's divided by 185. When you type this into your calculator, you don't have to do it in two steps. You can do it on one step. Just make sure that this guy right here goes in parentheses, and this guy right here goes in parentheses. So square root of 0.7188 times 0.2812 divided by 160. And then need another set of parentheses, so plus 0.8486 times 0.1514. Divided by 185, and I get 0.0442. 0.0442. Now a lot of people say, well, do I have to use 4 decimals? Could I use only 2 decimals there inside of for the p hats? Well, I mean, your difference is going to be very minute, but I would recommend using 4 decimals for accuracy. So the other thing I need is z star, and with proportions you always use z, and z star here would be 1.96 for 95% confidence, and that's just one of those ones you kind of have memorized. And here we go. So here was the difference we saw, and I'm going to add or subtract my margin of error, which would be 1.96 times 0.0442, and that margin of error is 1.96 times 0.0442 and 0.0866. So again, 0.1298 plus or minus 0.0866. Really been trying out the coffee for you guys. So that gives me a final interval of, let's see here, 0.1298 minus 0.0866, 0.0432, and 0.1298 plus 0.0866 is 0.2164. So this interval tells me that I am 95% confident that the true difference between men and women is anywhere from 4% to 21%, or maybe 22, maybe 4% to 22% higher for women. Notice that this whole entire interval shows, remember, we started off thinking that women were about 13% more likely, or 13% of more women wore their seatbelt. And now our interval shows that it could be as high as 22%, but it could be as low as 4%. And again, I'm rounding there just to say it, but that's the idea, is that it's definitely, the good news that we learned here is that it does seem that women are more likely to wear their seatbelt. I'm sorry. Anyway, it does seem that women are more likely to wear their seatbelt. How much more? 4% more or 22% more, all depending. So notice that it is definitely more. Now I want to kind of just demonstrate here. Let's just say that we did this and I added and I subtracted and I got something like negative 0.02 to positive 0.24. Now this would be interesting if this was the interval. It's not, but let's just say it was. Let's pretend here. This would show that women could be anywhere from 24% more than men to 2% less than men. So this interval would tell us that men could actually be more likely to wear their seatbelt than women. So that would tell us that, oh boy, we don't know who wears their seatbelt more. For crying out loud, the difference could even be zero, meaning there could be no difference between men and women. So that interval, if it happened, would tell us something very different than the one we found. So kind of cool. All right. Sorry. Let's talk about difference between two sample means now. So right idea here is that what do we need? Well, we need an average from a first sample and we need an average from a second sample, and we want to look at the difference between them. But what else do we need? Well, we also needed the standard deviation from that first sample, and we also need the standard deviation from that second sample, because in order to calculate the standard error of the difference between the two samples, and we have to understand that this is just our difference, and this is just our difference. Could be somebody else, Sarah or Tommy might have a different difference. So anyway, they're going to vary, and the formula needs the standard deviations of the populations for standard deviation, but unfortunately we only know our sample standard deviation. So here's the formula that we're going to use here. And this is for standard error, and that would be the standard deviation of the first sample squared divided by the sample size, plus the standard deviation of the second sample squared divided by the sample size. And if you look into your sampling distribution for the difference between two samples, it looks very familiar, except the standard deviation uses sigma 1 and sigma 2, but we don't know those. Don't forget to check your conditions again. Both samples got to be random, both samples have to be less than 10% of the population, and both samples have to be big enough. Make sure you show your work. We do need a T star here, and a little bit weird, but let me explain 1 second. First off, what you're going to do to find the interval is actually take the difference that you saw between the two samples, add or subtract a margin of error, and that margin of error is going to be T star times your standard error of the samples there, right? So pretty simple. Now, here's the problem. You have two samples. What do you use for degrees of freedom to find T star? So T star is found by looking it up on your degrees of freedom chart or your T chart. But what do you use for degrees of freedom? So I'm going to write that down right here. What you do is you do the first sample minus 1, and then you add to it the second sample minus 1. Now, that is one of many. Some people use a different formula where they just use the biggest of the, the biggest of the two. So they do sample size minus 1, sample size minus 1, whatever one's bigger. And there's actually even a more advanced, very complicated formula for degrees of freedom when you're working with two samples. But you know what? We're not even going to bother showing you guys that. You could just use this right here. Fairly simple. Sample size of the first minus 1 plus sample size of the second minus 1 for degrees of freedom. And then don't forget that third step of your nice conclusion. So once again, just like the previous problem, let's jump right into a problem here. Here we go. Sorry. Is there a difference between how much time overweight people spend eating a meal compared to those who are physically fit? A sample of 68 overweight people showed, sorry for the typo there, I must have did this really quickly, showed they spend an average of 18.36 minutes at the dinner table and a standard deviation of 3.6 minutes. And a sample of 80 physically fit people spent an average of 16.25 minutes with a standard deviation of 2.3. So we want to find out what's the real difference between how much time an overweight person spends at the dinner table versus a physically fit person. So let's go and just calculate a 95% confidence interval for that difference. Well, the first thing we need a difference for overweight people, so I'll use an O there for overweight, and that was, let's see here, 18.36. And then we need a difference for physically fit people. So I use a P there for physically fit. And that was 16.25. So what difference did we observe? Well, we observed a difference of 18.36 minus 16.25. We had an observed difference of the overweight minus the physically fit, observed difference of 2.11 minutes. Now, that's just what my two samples showed. Somebody else's sample showed me 1 minute. Somebody else's sample might show 3 minutes. So we want to know what the true difference is, and that's what we're trying to use the confidence interval to estimate. So the only other thing we need is the standard deviation of the overweight sample, which was 3.6, and the standard deviation of the physically fit sample, which is 2.3, and that's because we need those to calculate our standard error of the difference. And it's not a standard deviation because we're using the sample. Remember, that's why. And it's also why we have to use a T instead of a Z. But anyway, so we have 3.6 squared divided by the sample size of overweight was 68 people, plus 2.3 squared divided by the sample size of physically fit people, which was 80, it says. So here we go. And again, you could do all this at once. You don't have to do separate things. Just make sure that these things go in their own sets of parentheses here. So square root of 3.6 squared divided by 68 plus 2.3 squared divided by 80. And hopefully I have all those numbers right. Looks right. And I get 0.5067. And that would be in minutes as well. Both samples have to be random. Both samples have to be less than 10%. Now, please don't, say as I do as I say, not as I do. You know what I mean? I'm rushing through this so your video's not forever, but this should be a nice full census, both less than 10% of population, and both samples have to be big enough. Okay, whatever that means. Remember, we talked about that with the central limit theorem. All right, so anyway, now that we pretty much have everything we need, I mean, we really do. The only thing we need is a T star. So we do need to go ahead and grab our T chart here. And I have how many degrees of freedom? Well, I have 67 degrees of freedom from the first sample, and I got 79 degrees of freedom from the second sample. So, subtract 1, subtract 1. Add those together, it's 146 degrees of freedom total. Now, if you're using a T-chart, you don't have 146 on there. You're just going to have to go ahead and use 100. So 95% confident with 100 degrees of freedom would be 1.984. Let me write that down, 1.984. Now, if I go and use my calculator and do an invert T of 0.025, that's the tail probability for 95% confident, and actually type in 146, I get a little more precise. I get 1.976. So if you would use 1.984 from the chart or 1.976, you would get good enough answers that I would accept. Now, to be honest, there actually is another better estimate that uses a much more advanced formula, but don't worry about it. So here we go. We saw 2.1 minutes as a difference, 2.11 minutes as a difference, plus or minus the 1.984. T star times the 0.5067 standard error. So that's going to create my margin of error, 1.984 times 0.5067. And that is a margin of error of 1.0053. So I get 2.11 plus or minus the margin of error, which was 1.0053. So now I can calculate this. 2.11 minus 1.0053 gives me a bottom of my interval of 1.1047 minutes. And the top of my interval would be the same thing, but with a plus sign here. And that would be 3.1153. 3.1153. So this interval tells me that I'm 95% confident that the true difference between overweight people and physically fit people is that overweight people will be spend anywhere from 3.12 minutes more at the dinner table than physically fit people to 1.10 minutes more than physically fit people. So again, what I've learned is that regardless, the confidence interval with 95% confident, which is pretty good, and my sample sizes were fairly large, so hopefully I'm pretty precise here, is that there will be a difference. Overweight people do spend more time at the dinner table. It seems to make sense, but it seems pretty logical, but we did want to find an interval. Now, once again, let me just kind of talk about what we said before. Let's just say that the interval came back in at negative 1.3 to positive 3.4. Now, that didn't happen, but let's just say it did. This would actually say that physically fit people could be 1.3 minutes more at the dinner table, or overweight people could be 3.4 minutes more at the dinner table, or notice zeros in that interval, so that would tell me that they could even be tied, that there really is no difference between overweight people and how much time they spend at the dinner table and physically fit people and how much time they spend at the dinner table. So it's really important to understand that we're trying to see if there's a difference or not. And if we get an interval that contains zero, well, then that means that there might be no difference. So obviously we thought there was a difference between these two groups of people, but we realized, hey, there wasn't. So keep that in mind as you talk about, if you see more problems, because that may come up. So sorry the video was a little bit longer, but hopefully it was helpful to you, and we're going to do some problems like this in class on Tuesday. All right, enjoy the rest of your guys' weekend.